Reality might be far bigger than your eyes can see. The idea of hidden dimensions sounds like wild science fiction, yet it represents one of the most serious frontiers in modern physics. We are about to journey through 30 distinct theories that explore this incredible possibility, from the elegant mathematics of curled-up dimensions to the startling notion that our entire universe is a mere slice of a much grander cosmos. By the end, you will see the fabric of existence in a completely new light. We will uncover why gravity is so strangely weak and if black holes could be windows to other realms. What part of this hidden reality are you most curious to explore? The very first attempt to find hidden dimensions began with a simple and beautiful idea. In the early 1920s, a mathematician named Theodore Kaluza wrote to Albert Einstein with a remarkable proposal. He suggested that if we add a single extra dimension to the four we know, space and time plus a fifth, something incredible happens. The equations for gravity, described by Einstein's own general relativity, suddenly produced a second set of laws. They perfectly described the force of electromagnetism. It was as if gravity and light were two sides of the same cosmic coin, united by a dimension we simply could not perceive. This was the birth of Kaluza-Klein theory. But a glaring question remained. Where is this fifth dimension? Why can't we move through it? The answer came from physicist Oscar Klein. He proposed that this extra dimension is not vast and expansive like the others. Instead, it is curled up into an unimaginably tiny loop, a process known as compactification. Think of a garden hose stretching across a field. From a distance, it looks like a simple one-dimensional line. But get closer and you see its surface is a second dimension curled into a circular tube. An ant on that hose could walk along its length, or it could walk in a tiny circle around its circumference. We are like someone viewing the hose from far away, completely unaware of the tiny circular path. This compactification explains everything. The dimension is real, but it is so small, on a scale a billion trillion times smaller than an atom, that our most powerful instruments cannot detect it. This elegant idea from a century ago did more than just propose an unseen dimension. It provided the fundamental blueprint for all modern theories of extra dimensions, including string theory. It showed that the underlying geometry of reality could hold the keys to unifying the forces of nature. But what if these hidden dimensions are not just tiny but vast and infinite? Kaluza and Klein's single extra dimension was just the beginning. The next great leap came from a theory so radical it reimagined the very building blocks of the cosmos. This is string theory. Forget the idea of point-like particles. Instead, picture every single fundamental ingredient of reality, every electron and every quark, as an unimaginably tiny, vibrating loop or strand of energy. A string. What makes one particle different from another, what gives an electron its mass and a photon its light, is not its substance but the unique way its string vibrates. Think of a guitar string. Pluck it one way and you get a specific musical note. Pluck it differently and you get another. In this cosmic symphony, every distinct vibration of these fundamental strings produces a different particle. An electron is one note, a quark is another. The entire universe is a song played on these tiny, vibrating strings. But for this beautiful idea to work mathematically, for the cosmic symphony to be in tune, the strings cannot simply vibrate in the three spatial dimensions we know. The equations of string theory demand more room. They require extra dimensions for the strings to wiggle and resonate in all the necessary ways. The math points consistently to a universe with 10, or in some versions, 11 total dimensions. This means that woven into the fabric of our familiar four-dimensional spacetime are 6 or 7 additional hidden dimensions, all curled up into an intricate, compact shape. The specific geometry of this hidden dimensional landscape is everything. It acts like the body of a guitar or the interior of a grand piano. the shape of the instrument determines the possible resonant notes. In exactly the same way, the precise, complex shape of these curled-up dimensions dictates the possible vibrational patterns of the strings. This, in turn, determines the properties of the particles we observe, the forces they feel, and ultimately, the very laws of physics that govern our reality. The reason we have this particular set of particles and forces, and not another, might be a direct consequence of the hidden geometric shape of these unseen dimensions. So the search for a fundamental theory of everything becomes a search for the right geometry, the one shape that produces the cosmic song we call home. But if these dimensions are so crucial, could they ever be detected directly? String theory's many variations created a puzzle of their own. Physicists had 5 different, self-consistent versions of the theory, each demanding 10 dimensions, yet no single one could claim to be the final word. The breakthrough came with a powerful, unifying idea known as M-theory. Think of it as the master theory, a deeper framework that reveals the 5 string theories are not rivals. They are merely different windows into the same, grander reality. M-theory does not simplify the landscape, it expands it, proposing a universe founded on 11 dimensions. But it also introduces something even more profound to fill that expanded space, objects called branes. Short for membranes, a brane can be any dimensional object. A 0 brane is a point, a 1 brane is a string, a 2 brane is a sheet like a membrane. Our own universe with its 3 dimensions of space could be a 3 brane. This single idea transforms our cosmic address. We are not merely living in a universe with hidden, curled-up dimensions. We might be living on a vast, 3-dimensional island, a 3 brane, which itself is floating within a much larger, higher-dimensional reality called the bulk. All the matter we know, every atom and every light wave, could be stuck to the surface of our brain like ink on a page. This explains why we are so exquisitely tuned to only 3 spatial dimensions. We are made of particles that cannot leave the brain we call home, but one force is different. Gravity, in this picture, is not a force like the others. It is the geometry of spacetime itself, and geometry is not confined to a brain. The fabric of spacetime permeates the entire bulk. This leads to a stunning possibility. The gravitational force generated by the matter on our brain could be leaking away, spreading out into the unseen extra dimensions of the bulk. Picture a world where sound is trapped on the surface of a lake, but ripples can travel deep into the water below. We are the creatures on the surface, hearing only the sound, completely unaware of the energy fading into the depths. This gravitational leakage could be the answer to one of physics' oldest mysteries. Why is gravity so incomparably weak? A tiny magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. The reason might be that gravity is not inherently weak. It is simply diluted, its true strength spread thin across dimensions we cannot access. But what if our universe was born not from a single, solitary explosion, but from a shattering collision? This is the core of the ekpyrotic universe theory, a radical alternative to the Big Bang that replaces a primeval singularity with a cosmic crash. In this brain world picture, our 3-dimensional universe is one of many vast sheets adrift in the higher dimensional bulk. The Big Bang, the moment we point to as the beginning of everything, was not the beginning at all. It was the moment our brain collided with another parallel brain. Picture 2 enormous, perfectly flat sheets of rubber floating silently in an immense dark space. Over eons, they drift toward one another, drawn together by a force threading through the bulk. When they finally meet, the impact is not destructive but creative. The colossal transfer of kinetic energy into our brain manifests as an intense, uniform heat and a rapid expansion. Every particle of matter, every quantum of radiation that would one day form galaxies, stars, and us, was forged in that fiery collision. This theory elegantly solves 2 of cosmology's greatest puzzles, the horizon problem and the flatness problem without needing a period of rapid inflation. The horizon problem asks why the universe looks the same in all directions. Regions of space far apart seem never to have been in contact, yet they share the same temperature and properties. Inflation solves this by having space expand faster than light, allowing these regions to have been in touch before the expansion. The ekpyrotic model offers a different answer. Before the collision, the two branes were parallel and very close together for a long time. This prolonged period of proximity allowed energy and information to equilibrate across the entire surface of our brain, creating a perfectly uniform starting condition. The flatness problem questions why the geometry of our universe is so perfectly balanced, neither positively nor negatively curved. The ekpyrotic scenario naturally produces this flatness. The collision between two incredibly flat, parallel branes can only result in a universe that is itself incredibly flat. The most profound implication, however, is the cyclic nature of this cosmos. After the collision, the branes move apart, stretched and energized, but the force that drew them together eventually pulls them back, setting the stage for another collision, another Big Bang, and another universe. In this view, our universe is not a one-time event. It is one act in an endless cosmic cycle of creation, destruction, and rebirth, playing out across the hidden dimensions of the bulk. What if the hunt for hidden dimensions is not a search for the impossibly small, but for something almost within our grasp? This is the bold proposal of the large extra dimensions theory, put forward by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Jorge De Valle. They turned the Kaluza-Klein idea on its head. Instead of all extra dimensions being curled up at a microscopic scale, what if one or two of them were comparatively enormous, as large as a fraction of a millimeter? In our daily lives, we would never notice a dimension this size. The forces that govern our world, the electromagnetic force that holds atoms together and the nuclear forces, are still trapped on our three-dimensional brain. We are like flatlanders living on a vast sheet, unaware of the spacious room just above our heads, but gravity is different. It bleeds into the bulk. If there are large extra dimensions, the true strength of gravity is not what we measure. The gravitational field our planet generates would not be confined to our three-dimensional space. It would spread out or dilute into these large, unseen dimensions. Think of a drop of ink falling onto a small, dense sponge. The ink concentrates in a small, dark spot. Now imagine that same drop falling onto a huge, fluffy pillow. The ink spreads out, becoming a faint, wide stain. We are measuring the faint stain, and that is why gravity seems so weak. Its full power is simply leaking into a larger volume of space. This leads to a thrilling and testable prediction. If we can probe the universe at incredibly small distances, at the scale where these large extra dimensions become significant, we should see gravity behave differently. It should suddenly become as strong as the other fundamental forces. Particle colliders like the Large Hadron Collider are our windows into this realm. By smashing particles together with immense energy, we create conditions that can, for a split second, explore this tiny, high-gravity regime. Scientists are actively searching for two potential signatures. The first is the sudden disappearance of energy. This could signal the production of a graviton, the hypothetical particle of gravity, which immediately carries its energy off into the extra dimensions, vanishing from our detectors. The second signature is even more dramatic. If gravity becomes truly strong at these tiny scales, the colliding particles could concentrate enough energy to warp space so violently that they create a microscopic black hole. This would not be a planet-devouring monster. It would be an ephemeral speck, evaporating in a flash of Hawking radiation almost instantly after it forms. Its detection would be the ultimate proof that our universe is not what it seems, that our reality is a thin slice embedded within a far grander and much larger hidden architecture. The strength of gravity is not a fundamental constant but a local illusion. This is the radical promise of the Randall-Sundrum model, which proposes that the very fabric of the extra dimensions is not flat but deeply warped. Picture a vast flexible sheet. Now imagine that this sheet is curved into a steep funnel or a deep valley. This is the shape of the warped extra dimension. Our universe, our three brane, sits at the thin, narrow end of this funnel. Far, far away at the wide mouth of the funnel sits a second brane, which we might call the gravity brane. The fundamental strength of gravity is generated there at that distant shore, but by the time its influence travels across the warped geometry to reach our brane, it has been exponentially diluted, weakened by the immense curvature of the space between us. The warping acts like a cosmic damper, suppressing gravity's true power. This single, elegant idea solves one of physics' most stubborn puzzles, the hierarchy problem. Why is the force of gravity so many orders of magnitude weaker than the other fundamental forces? The answer is not that gravity is weak, but that we live in a region of space where it is naturally filtered to a faint whisper. All the other forces, like electromagnetism, are confined to our brain and remain at full strength. The most mind-bending implication of this model is the possibility of an infinite extra dimension. Unlike the compactified dimensions of string theory, this fifth dimension could be truly endless, yet we would never be able to access it or even perceive its infinity. The intense warping of space itself acts as a gravitational prison, trapping all particles and forces except for gravity on our local brane. We are like sailors on a raft, adrift on a boundless ocean, but the very nature of the water prevents us from ever leaving the raft. We can only observe the gentle lapping of the waves, the diluted effect of the infinite sea around us. This warped geometry provides a completely new way to think about our confinement within a three-dimensional reality, not by the small size of other dimensions, but by the sheer shape of the cosmos itself. Every known particle in the cosmos might have a hidden, silent twin. This is the elegant and powerful idea of supersymmetry, a concept deeply woven into the fabric of string theory and the quest for hidden dimensions. Supersymmetry, often called SUSY, proposes a fundamental partnership in nature. For every particle of matter, like an electron or a quark, there should exist a superpartner, a force-carrying particle. And for every force-carrying particle, like a photon, there should be a superpartner that is a matter particle. These superpartners would be far more massive than their familiar twins, which is why we have not yet detected them. Their existence is not just a neat addition, it is essential for the mathematical consistency of string theory. Those 6 or 7 curled-up dimensions require supersymmetry to remain stable. Without the balancing effect of these superpartners, the intricate geometric shapes that define our physical laws would simply unravel, collapsing into an unstable mess. The hunt for these superparticles is therefore a hunt for the very architecture of hidden dimensions. The Large Hadron Collider is our most powerful tool in this search. When protons collide at near light speed, they concentrate immense energy, and physicists hope to see a telltale signature of a supersymmetric particle being created. It would appear as a significant amount of missing energy in the detectors, energy carried away by the lightest and most stable superpartner, which would be invisible to our instruments. This leads to one of the most profound implications of supersymmetry. That stable, invisible superpartner is a perfect candidate for the mysterious substance known as dark matter. The ghostly halo of dark matter that holds galaxies together could be made of these primordial supersymmetric particles left over from the universe's violent birth. So the search for supersymmetry is a triple quest aiming to stabilize the hidden dimensions of string theory, complete the particle family, and finally identify the invisible majority of our universe's mass. These intricate, 6-dimensional shapes are the hidden engines of string theory. They are known as Kaluza-Klein manifolds, and their geometry is the final piece of the puzzle for how 10-dimensional strings produce our 4-dimensional world. Imagine the 6 extra dimensions required by string theory are not just 6 tiny circles, but are curled up into one of these profoundly complex shapes. A Kaluza-Klein manifold is not a shape you can easily picture, a multi-dimensional object with a topology full of holes, twists, and tunnels. If you could shrink down to the quantum scale and peer into the heart of space, you would not find emptiness. You would find this breathtaking, labyrinthine structure woven into the very fabric of reality. The specific form of this manifold is everything. Think of it as the cosmic equivalent of a musical instrument with an impossibly complex interior. A violin and a trumpet, even when playing the same note, produce distinct sounds because of their unique shapes and internal chambers. In exactly the same way, the precise geometry and topology of a Kaluza-Klein manifold determine the resonant vibrations of the strings. The number of holes in the shape, the types of folds it possesses, these mathematical features directly dictate the number of distinct vibrational patterns that are possible. Each allowed vibration corresponds to a different fundamental particle. So, the number of holes in the Kaluza-Klein manifold could determine how many generations of electrons and quarks exist in our universe. Its intricate curves could fix the masses of those particles and the strengths of the forces they feel. In this view, the laws of physics are not fundamental rules written on a cosmic tablet. They are emergent properties, the unique output of a specific, hidden geometric shape. This leads to a staggering possibility, the string theory landscape. There is not just one possible Kaluza-Klein manifold. Mathematics allows for a colossal number of them, perhaps 10 to the 500 different versions or more. Each one represents a different possible vacuum state, a different set of physical laws, and a different possible universe. In one manifold, the vibrational patterns might produce a universe with 4 fundamental forces and 3 families of quarks, just like ours. In another, the patterns could yield a cosmos with completely different particles and forces, a reality where chemistry is impossible or gravity is repulsive. Our universe, with its particular constants and conditions, may not be special or fine-tuned. It might simply be one possible outcome among an almost infinite array of mathematical possibilities, a single cosmic song that can be played on one specific Kaluza-Klein instrument. The search for our universe then becomes a search for the one shape whose hidden symphony matches every particle we have ever observed. Our 3-dimensional reality might be nothing more than a magnificent illusion. This is the astonishing claim of the holographic principle, which suggests that our universe, with all its depth and volume, could be a hologram projected from a 2-dimensional surface. The idea seems to defy all common sense, yet it emerges from the most rigorous study of the most extreme objects in the cosmos, black holes. When physicists studied black hole thermodynamics, they made a startling discovery. The maximum amount of information, the entropy, that a black hole can contain is not proportional to its volume as you might expect. It is proportional to the surface area of its event horizon. This is profoundly strange. Imagine a storage device like a hard drive. The data it holds should scale with its 3-dimensional volume. But for a black hole, the ultimate storage container, all the information needed to describe every star, planet, or person that falls in is somehow encoded on its 2-dimensional boundary. This hinted at a radical new law of physics, that the information content of any region of space is defined by its surface area, not its volume. The universe itself might operate like a cosmic hologram. The 3 dimensions we experience could be a projection from a vast, swirling sea of quantum information stored on a distant, 2-dimensional shell that encloses us. A concrete mathematical realization of this principle came from physicist Juan Maldacena. He discovered the anti-de Sitter/conformal field theory correspondence, often abbreviated as ADS/CFT. This is a powerful duality, a kind of dictionary that translates the physics of a hypothetical universe with gravity in its interior, which has a certain negative curvature, into the physics of a quantum field theory without gravity that lives on its lower dimensional boundary. In simpler terms, it shows that a complex gravitational universe with extra dimensions can be perfectly and completely described by a quantum system that has one less dimension and no gravity at all. It is as if the entire, rich three-dimensional world inside a bubble, complete with stars, planets, and the force of gravity, is nothing more than a sophisticated projection from information dancing on the two-dimensional surface of the bubble itself. This is not just a metaphor, it is a precise mathematical equivalence proven in a specific, though hypothetical, universe. The profound implication is that information may be the most fundamental ingredient of reality, more fundamental than space or time. If our universe is holographic, then the solidity of the world around us, the feeling of depth and distance, is an emergent phenomenon, a grand illusion generated by an unimaginably complex calculation happening at the boundary of our perception. We are not just in the universe, we may be a projection of it. The deepest conflict in modern physics is a war of scales. On one side, we have quantum mechanics, which masterfully describes the chaotic, probabilistic world of the very small. On the other, we have Einstein's general relativity, which paints a smooth, geometric picture of gravity and the cosmos. The two theories are brilliant, yet they refuse to speak the same language. They break down completely when forced to describe the same event, like the center of a black hole or the first moment of the Big Bang. This is where the idea of hidden dimensions offers a breathtakingly elegant peace treaty. By allowing gravity to operate in a higher dimensional space, its fundamental quantum nature could become far easier to describe. In the vastness of the bulk, the sharp, point-like singularities predicted by relativity might smooth out. The violent quantum fluctuations that shatter our four-dimensional equations could find the room they need to resolve into a coherent, unified picture. This is the promise of extra dimensions for quantum gravity, a framework where the fabric of space-time itself is woven from threads that extend into realms we cannot see. Not every path to quantum gravity requires extra dimensions, however. A rival approach called loop quantum gravity takes a different path. It suggests that space itself is not a continuous background, but is quantized, woven from a fabric of tiny, finite loops. In this view, the universe has a discrete, atomic structure at the smallest possible scale, the Planck length. This theory brilliantly avoids the mathematical infinities that plague other attempts, but it does so by remaining firmly in our familiar three dimensions of space and one of time. The existence of extra dimensions would not necessarily disprove loop quantum gravity, but it would demand a profound expansion of its core idea, asking what the quantum structure of those additional directions might be. Perhaps the most startling connection between extra dimensions and quantum theory involves one of its greatest mysteries, quantum entanglement. Einstein famously called it spooky action at a distance, where two particles become linked in such a way that measuring one instantly influences the other, no matter how far apart they are. This seems to violate the cosmic speed limit set by light. But what if that spooky connection is not a message traveling through our three-dimensional space? What if the particles are, in fact, touching in a higher dimension? Imagine two characters drawn on separate pages of a book. To the characters, they are isolated in their two-dimensional worlds. But you, holding the book, can see that their pages are connected by the three-dimensional spine. From your higher dimensional perspective, they are neighbors. In a similar way, two entangled particles might be infinitesimally close to each other when measured through a hidden, compact dimension. Their instantaneous link is not a signal, but a reflection of a deeper, geometric unity in the full architecture of reality. The spooky action is not happening at a distance in our space. It is happening because there is no distance at all in the full, higher dimensional bulk. This dimensional hopping offers a profound new way to visualize the quantum world, suggesting that the true, complete picture of reality requires us to step outside the three-dimensional stage we call home. Brain cosmology completely rewrites the first chapter of our universe's story. The violent beginning we call the Big Bang might not have been a singular explosion in a void, but a cataclysmic event echoing from a higher dimensional reality. In this picture, our three-dimensional brain could have been born from a collision with a neighboring brain, a shattering impact that infused our reality with all the heat and energy we now observe as the cosmic microwave background. This brain collision scenario offers a powerful alternative to cosmic inflation. Instead of a mysterious field causing space to expand faster than light, the uniform temperature and flatness of our universe could be natural consequences of two flat, parallel brains interacting over vast stretches of higher dimensional time. The energy of their collision naturally creates a hot, dense, and perfectly smooth starting condition, but the influence of the bulk does not end with creation. The mysterious force driving the universe's accelerated expansion, dark energy, might also have its origins in the geometry of the hidden dimensions. The vacuum energy on our brain could be interacting with the bulk, or perhaps the brain itself is being gently pushed apart by forces from other dimensions. Imagine our universe as a sheet of paper floating on the surface of a pond. The way it moves and stretches could be determined not just by its own properties, but by subtle currents and pressures from the deeper water below. In brain cosmology, dark energy is not necessarily a strange new substance. It could be the long-range gravitational pull of another, parallel brain in the bulk, slowly drawing our own universe outward and accelerating its expansion. This framework transforms our cosmic history from a solitary event into a dynamic, multidimensional narrative, where the deepest mysteries of our universe's birth and ultimate fate are written in the invisible architecture of the higher dimensional space we are embedded within. The sheer number of possible Kaluza-Klein shapes leads us to a staggering conclusion: the multiverse. Each distinct way of curling up those 6 hidden dimensions does not just create a different set of particles, it forges an entirely new set of physical laws. The strength of gravity, the mass of an electron, the very number of dimensions that appear large and stable, all of these are determined by the geometry of that hidden space. We are not talking about different galaxies within one cosmos, but entirely separate pocket universes, each with its own unique dimensional architecture and fundamental constants. This is the string theory landscape, a cosmic archipelago of possible realities so vast that the number of distinct vacuum states could be 10 to the power of 500. That number is beyond astronomical. It is an almost meaningless expanse of possibility. In one such pocket universe, the compactification might yield 4 large dimensions, but with a much stronger nuclear force, causing all stars to burn out in a fleeting instant. In another, the vibrational patterns of the strings might not allow for atoms to form at all, resulting in a barren, particle-less void. Our universe, with its 3 spatial dimensions and its precise, life-allowing constants, is just one single garden in this infinite cosmic wilderness. This brings us to a deeply philosophical question: the anthropic principle. Why does our universe seem so finely tuned for our existence? If the strength of gravity were slightly stronger, stars would collapse too quickly. If the electromagnetic force were slightly weaker, atoms would not bond. The answer from the landscape is both humbling and liberating. In a multiverse where every possible set of laws is realized somewhere, it is no surprise that we find ourselves in one of the rare pockets where the conditions are just right for stars, planets, and life to form. We do not live in a special universe, we live in a viable one. Our presence here is not a proof of design, but a consequence of probability. We are the cosmic observers who can only exist in a corner of the landscape where the hidden dimensions curled up in exactly the right way to sing our specific song of reality. The hunt for these unseen dimensions has moved from pure mathematics into the tangible world of experimental physics. scientists are now designing ingenious tests to find the fingerprints of a larger reality. Some of the most direct searches look for gravity's behavior at incredibly small distances. If there are large extra dimensions, gravity should stop following its familiar inverse square law and become stronger when probed at sub-millimeter scales. To test this, researchers use exquisitely sensitive tabletop experiments. Imagine a device no bigger than a shoebox with tiny, suspended mirrors and finely tuned lasers. It measures the gravitational pull between minuscule weights separated by a gap smaller than the width of a human hair. These experiments are hunting for any deviation, any tiny surge in the gravitational force that would signal gravity is spilling into a hidden dimension just beyond our everyday perception. So far, gravity has behaved impeccably, but the search continues, pushing into ever smaller distances where the hidden architecture of space might finally reveal itself. On a much grander scale, the world's most powerful particle accelerator is probing the quantum frontier for dimensional leaks. At the Large Hadron Collider, protons are smashed together at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. Physicists meticulously analyze the debris of these collisions, searching for two telltale signs of extra dimensions. The first is missing energy. When two particles collide, the total energy before and after must be equal. But if the collision creates a graviton, the hypothetical particle that carries gravity, and that graviton immediately escapes into a hidden dimension, it would vanish from our detectors. The event would show a significant, inexplicable deficit of energy, a clear signal that something carried it away into the bulk. The second signature is even more dramatic. If the energy of the collision is concentrated enough within the tiny volume where gravity becomes strong, it could warp space so violently that it pinches off into a microscopic black hole. This ephemeral object would not be a threat. It would evaporate in a flash of radiation in less than a billionth of a trillionth of a second. But its detection would be undeniable proof of extra dimensions, a direct creation from the deeper gravitational reality that surrounds us. The search extends far beyond our planet into the cosmos itself. Ultra-high-energy cosmic rays, atomic nuclei traveling from distant galaxies with energies far beyond what any human-made accelerator can produce, constantly bombard our atmosphere. When they strike air molecules, they create showers of secondary particles. Some theories suggest that if extra dimensions exist, these cosmic rays could produce a telltale pattern in their showers, or even create microscopic black holes high in the atmosphere, offering a natural, cosmic version of the LHC experiments. Even the ripples in spacetime itself, gravitational waves, could carry secrets about the universe's true shape. When two massive objects like black holes or neutron stars spiral into each other, they send out waves that stretch and compress space. As these waves travel across the cosmos, could they subtly interact with the hidden dimensions? Future, more sensitive gravitational wave detectors might be able to discern tiny distortions in the signal, a faint echo resonating from the bulk, revealing that spacetime has more layers than we ever dreamed. Each of these experimental paths offers a potential key, a way to move the question of hidden dimensions from the blackboard into the realm of observable, testable fact, forever changing our understanding of where we truly live. Empty space is not truly empty. Even in the deepest vacuum at the absolute zero of temperature, the quantum world is a seething, bubbling sea of activity. Virtual particles flicker in and out of existence, their fleeting lives governed by the uncertainty principle. This quantum frenzy generates a subtle pressure, and it is this pressure that creates one of the most peculiar forces in physics, the Casimir effect. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, so close they are almost touching. Outside the narrow gap between them, a whole spectrum of virtual particles can pop into being. But inside the gap, only certain wavelengths of this quantum activity can fit, much like how only specific musical notes can resonate inside a flute. This imbalance in quantum pressure outside versus inside pushes the plates together, creating a measurable, irresistible force. It is a ghostly hand born from the activity of nothingness pushing the plates into contact. This confirmed prediction of quantum theory is strange enough, but it could be the key to unlocking a far greater mystery. The calculations that predict the precise strength of the Casimir force are based on our familiar 3 dimensions of space. But what if those calculations are incomplete? What if the virtual particles flickering in and out of existence are not just doing so in our 3 dimensions, but are also appearing in hidden, compact dimensions? The presence of these extra realms would open up new channels for quantum activity. The sea of virtual particles would have more room to fluctuate, altering the subtle pressure balance between the plates. In a universe with large extra dimensions, the Casimir force would be stronger than our standard models predict. The ghostly hand would push with more power than it should. This makes the humble Casimir effect a potential window into the cosmic bulk. Scientists are now conducting exquisitely precise tabletop experiments to measure the Casimir force at microscopic separations. They use incredibly flat plates, advanced lasers, and painstaking calibration to see if the force matches the 3-dimensional prediction or if it reveals a telltale enhancement. Any consistent deviation, any extra push that cannot be explained by known physics, would be a monumental discovery. It would suggest that the quantum fluctuations we observe are not confined to our visible reality. They are the surface ripples of a deeper, more dimensional quantum ocean, and we are just beginning to feel its true depth. A stubborn cosmic discrepancy has challenged our understanding of gravity for decades. When we observe the outer regions of galaxies, the stars are orbiting so fast that they should be flung out into the void. The visible matter alone does not provide enough gravitational glue to hold them together. The prevailing solution is dark matter, a vast halo of invisible particles surrounding every galaxy. But another, more radical idea asks a different question. What if we are not missing matter but misunderstand gravity? This is the core of modified Newtonian dynamics, or MUND. It proposes that on the immense scales of galaxies, gravity stops following Newton's familiar laws and becomes slightly stronger. This extra gravitational kick would explain the rapid orbits without needing any invisible matter. For years, this was a fringe alternative, a simple adjustment to an old equation. But now, a profound possibility emerges. Could this modification be a clue to the universe's hidden architecture? What if gravity seems to change on galactic scales, not because the law is wrong, but because we are seeing its true, higher dimensional nature? In a universe with large extra dimensions, gravity's force weakens as it spreads into the bulk, but this dilution might not be uniform across all distances. On the scale of a solar system, gravity behaves as we expect, yet when you reach the vast, low-density frontiers of a galaxy, the gravitational field could begin to interact with the geometry of the bulk in new ways. The weakening of gravity might itself be weakened, effectively making it stronger relative to our 3-dimensional predictions at those immense scales. It would be like discovering that a leak in a pipe is not constant, but changes with the water pressure, revealing the complex shape of the pipe itself. The galactic rotation curves that dark matter so elegantly explains could, in fact, be the first observable map of a hidden dimension. The debate between dark matter and MUND is one of the great scientific rivalries. Dark matter is a powerful concept, successfully modeling the growth of the entire cosmic web. We see its gravitational fingerprints in the bending of light around galaxy clusters and in the patterns of the early universe. MUND, by contrast, has struggled to explain these larger-scale phenomena without adding its own special ingredients. But the recent connection to higher dimensional theories offers a thrilling synthesis. Perhaps dark matter is not a substance but a signal. The phenomena we attribute to an invisible particle could be the collective effect of gravity operating in a reality with more than 3 spatial dimensions. Researchers are now exploring this bridge, constructing brain world models where the gravitational field on our brain is naturally modified, producing effects identical to those of dark matter. The search is on for a precise signature that can distinguish between a halo of particles and a whisper from the bulk. The true nature of gravity and the reality of the dimensions we call home may ultimately be decided by the silent, swift dance of stars at the edge of the night. We have always accepted time as the fourth dimension, but what if it is not alone? Some of the most speculative theories in physics propose the existence of additional time-like dimensions. In our everyday experience, time is a one-way street, a single axis from past to future. Yet mathematically, the equations do not necessarily forbid a universe with two or even more independent time directions. Imagine having not just one clock but two, each measuring a different kind of temporal flow. One might govern the evolution of particles, while another dictates the unfolding of forces. Such a reality would possess a depth of causality we can scarcely comprehend. The most immediate and troubling consequence of multiple time dimensions is the potential for closed time-like curves. In a universe with more than one time, an object's world line could loop back on itself, creating a path that returns to its own past. This is not mere time travel to a fixed date, but a chaotic landscape where cause and effect could become utterly meaningless. An event could be its own cause, creating paradoxes that unravel the logical consistency of reality itself. This is the primary reason most physical models strongly prefer extra-spatial dimensions. Space provides a stable, orderly stage for events to play out. Time, in its multiplicity, introduces a volatility that most theorists find too destructive for a coherent universe. Yet the idea persists because of its potential payoffs. With multiple times, the laws of physics could become far richer, allowing for a more complex and nuanced description of quantum mechanics and gravity. The behavior of strings and branes could be described with greater symmetry, potentially leading to a more elegant unification. The challenge for physicists is to find a way to harness this theoretical power while somehow taming the chaos, perhaps by having the extra time dimensions compactify in a way that prevents macroscopic time loops, restricting their bizarre effects to the imperceptibly small quantum realm. Ultimately, our single arrow time may be the key to our existence, a necessary constraint that keeps reality from collapsing into an indecipherable tangle of possibilities. Our journey into the quantum realm reveals a space that is far from smooth. At the very smallest scales, the fabric of the cosmos might not be a neat three-dimensional grid, but a chaotic, infinitely complex fractal. This is the theory of fractional dimensions, a concept that challenges our most basic intuition about reality. We are accustomed to thinking in whole numbers. A line has one dimension, a plane has two, a volume has three. But what if space itself has a fractional dimension like 2.37? This is not a mathematical curiosity. It is a serious proposal for how to tame the violent infinities that plague quantum physics. In quantum field theory, when physicists calculate the interactions of particles, the equations often produce nonsensical, infinite results. The process of removing these infinities, called renormalization, can feel like a mathematical trick. But if space has a fractal nature at the quantum scale, these infinities might never arise in the first place. Imagine zooming in on a coastline. From a distance, it seems like a simple one-dimensional line. But as you get closer, you see bays, then inlets, then rocks, then grains of sand. The closer you look, the more detail and length you discover. A fractal coastline effectively has a dimension between 1 and 2. It is more than a line but less than a full plane. Now apply this to the vacuum of space. What we perceive as a smooth, three-dimensional void might, under extreme magnification, reveal an endless, crinkled structure. A particle moving through this fractal foam would not travel a straight path. Its journey would be so tortuous, winding through an infinite cascade of detail, that its effective journey is through a dimension that is not a whole number. This fractional dimensionality naturally suppresses the violent quantum fluctuations that lead to those troublesome infinities. The equations become well-behaved because the jagged, complex nature of space itself provides a physical cutoff, a fundamental graininess that smooths out the math. The universe at its heart may not be built from whole numbers, but from an endless fractional intricacy that holds the key to a consistent and complete theory of quantum gravity. A universe without a fixed scale is a universe of pure relation. This is the profound idea behind conformal symmetry, a principle where the laws of physics remain unchanged even if you stretch or shrink all distances uniformly. It is scale invariance, a world without an absolute ruler. This abstract symmetry finds its most powerful application in conformal field theory, a framework that describes the physics of systems, like the critical point of a magnet or certain quantum fluids where scale does not matter. But its true magic is revealed in its connection to the hidden architecture of our cosmos. Certain two-dimensional conformal field theories are not just descriptions of flat, simple worlds. Through a mathematical miracle known as duality, they are completely equivalent to the physics of a universe with gravity in a higher dimensional, warped space. This is the heart of the AD/CFT correspondence, the complex gravitational dance of strings and particles in a volume with an extra dimension is perfectly mirrored by the scale-invariant quantum dance happening on its lower dimensional boundary. It is as if the entire, rich three-dimensional world inside a spherical room, complete with its own gravity and hidden dimensions, is nothing more than a sophisticated hologram generated by information and interactions confined to the two-dimensional walls. This duality is not a vague analogy but a precise mathematical dictionary, where every entity in the higher dimensional gravitational theory has a direct translation into an operator in the lower dimensional conformal field theory. This relationship is foundational to string theory, providing its most concrete realization of the holographic principle. The takeaway is staggering. The phenomenon of scale invariance we observe in certain quantum systems might be far more than a curious property. It could be a direct clue, a ghostly imprint of a deeper dimensional structure. When a physical system becomes scale invariant, losing all memory of absolute size, it might be tapping into its true nature as a projection from a reality with more dimensions. The perfect, self-similar patterns of a fractal coastline, which look the same at any magnification, could be a faint echo of this fundamental truth. The absence of a scale in one reality hints powerfully at the presence of an entirely separate, larger reality from which it is projected. A black hole is a tear in the fabric of space-time, and that fabric might have more threads than we can see. These cosmic voids could be our most powerful windows into the universe's hidden architecture. Within their event horizons, the known laws of physics break down, and the true, higher dimensional nature of reality might be laid bare. One of the greatest puzzles is the black hole information paradox. Quantum mechanics insists that information is never truly destroyed, yet a black hole appears to swallow matter completely and then evaporate away via Hawking radiation, seemingly erasing that information forever. This contradiction points to a fundamental flaw in our understanding. Extra dimensions could offer a stunning resolution. What if the information is not lost inside the black hole, but is instead encoded on its surface or even transferred into another dimension? In the holographic principle, all the data about what fell in is preserved on the event horizon's two-dimensional surface. But in a brain world scenario, the information might not even be in our universe anymore. The intense gravitational collapse could create a bridge, a wormhole, connecting our brain to another in the bulk. The information would simply be somewhere else, not destroyed. String theory provides even more intricate possibilities. It predicts that black holes are not simple points of infinite density, but complex, higher dimensional objects called fuzzballs. A fuzzball is a giant, tangled knot of strings and branes, its structure defined by the precise way the extra dimensions are curled up. This intricate object has no singularity at its center. Instead, it has a defined, albeit wildly complex, surface that stores all the information of the matter that formed it. When the black hole evaporates, this information is slowly and carefully released in the Hawking radiation, resolving the paradox entirely. This means the most terrifying objects in the cosmos are not bottomless pits, but incredibly dense, information-saturated structures, their true form only visible in the full spectrum of higher dimensions. This leads to a thrilling prospect for astronomers. When two black holes merge, they release titanic gravitational waves. The specific ring-down, the way the new, larger black hole settles into its final shape, carries an imprint of its structure. If black holes are higher dimensional fuzzballs, or if their gravity is leaking into the bulk, their gravitational wave signatures would be subtly different from the predictions of standard four-dimensional general relativity. As our detectors become more sensitive, we might one day listen to the echo of a colliding black hole and hear, in the quiet fade of its space-time vibrations, the distinct whisper of a hidden dimension. The accelerating expansion of our universe could be a message from another dimension. Dark energy, the mysterious force driving this cosmic speed-up, remains the greatest enigma in modern cosmology. Why is the vacuum of space filled with this faint, repulsive energy, and why is its value so incredibly small? This is the cosmological constant problem. If we calculate the energy of the quantum vacuum using our known theories, the result is a number 120 orders of magnitude too large. That is a 1 followed by 120 zeros. A discrepancy this vast is not a minor error. It is a screaming clue that we are missing something fundamental about reality. The answer might be that our calculation is wrong because it assumes all that vacuum energy is confined to our three-dimensional brain. In a higher dimensional universe, the story changes completely. One compelling idea is that the true gravitational effect of our vacuum energy is not felt solely on our brain. It leaks into the bulk, diluting its apparent strength. Picture a sponge soaking up a spill. The water is still there, but it is spread throughout the sponge's structure, making the surface seem less wet. In the same way, the immense vacuum energy predicted by quantum theory could be spreading into the compactified dimensions, leaving only a faint residue that we measure as dark energy. This leakage provides a natural mechanism to suppress the cosmological constant to the tiny value we observe. Another possibility lies in the dynamic nature of the hidden dimensions themselves. What if the compactified Kaluza-Klein shapes are not static, but are slowly evolving over cosmic time? As these six-dimensional manifolds gradually shift and change their geometry, the effective vacuum energy they project onto our four-dimensional world could also change. The acceleration we see today might not be a permanent feature of the cosmos, but a transient phase in a much longer evolution. In some string theory models, this slow relaxation of the extra dimensions naturally produces a small, positive cosmological constant that drives acceleration, much like a settling fog reveals a landscape. The dynamics of branes offer a third, breathtaking explanation. Dark energy might be the gentle pressure from a parallel brane in the bulk. If another vast, three-dimensional world is floating relatively close to ours in a higher dimensional space, its long-range gravitational pull could be gently pushing our universe apart. We would not feel this force locally, any more than a sailor on the ocean feels the gravitational pull of the moon. But on the grandest scales, its cumulative effect would manifest as a universal repulsion, an acceleration etched into the history of the cosmos. Each of these theories transforms dark energy from a bizarre substance into a geometric phenomenon. It is not a thing, but a symptom, a shadow cast by the true, higher dimensional architecture of reality. The fate of the universe, whether it expands forever or eventually contracts, may ultimately depend on the silent, unseen evolution of dimensions hidden in plain sight. The mathematics governing every known particle has a hidden, higher dimensional shadow. Quantum field theory is the framework that describes particles as excited states of invisible fields, and it can be extended into worlds with more than 3 spatial dimensions. When it is, the consequences are profound. A particle existing in a universe with a compactified extra dimension, like the tiny circle proposed by Kaluza-Klein, cannot simply be itself. Its field must wrap around that hidden circle, and just like a guitar string, it can only vibrate at specific, resonant frequencies. Each of these allowed vibrations corresponds to a distinct particle from our 4-dimensional perspective. This cascade of higher dimensional echoes are known as Kaluza-Klein modes. An electron traveling in 5 dimensions would appear to us as an entire tower of progressively heavier partner particles, each one a different harmonic of the electron's fundamental vibration in the unseen dimension. Their masses are dictated directly by the size of the compactified space. The smaller the circle, the higher the energy required for these excited states, and the more massive these partner particles become. This mechanism does not just create new particles, it fundamentally alters the forces between them. The couplings, the strengths with which particles interact, are also shaped by the geometry of the hidden dimensions. A force that seems to have a single, fixed strength in our 4-dimensional view might, in the full higher dimensional reality, have its intensity diluted or focused depending on how its field spreads through the compactified space. This leads to a radical possibility known as universal extra dimensions. In this scenario, it is not just gravity that feels the bulk. Every force, from electromagnetism to the strong and weak nuclear forces, propagates through the full higher dimensional volume. All matter and energy are free to move in the grander cosmos. In such a universe, every single particle we know would have its own tower of Kaluza-Klein partner particles. The entire standard model of particle physics would be just the ground floor of an infinitely tall, multidimensional skyscraper. How could we ever detect such a subtle architectural shift? The answer lies in precision. The existence of these heavy partner particles would create tiny, virtual loops in quantum interactions, subtly shifting the predicted properties of the familiar particles we can measure. The magnetic moment of the muon, a property so precise it has been measured to 9 decimal places, is a perfect example. The theoretical calculation of this value could be minutely altered by the virtual influence of its own Kaluza-Klein tower. Any persistent, unexplained discrepancy between the exquisitely precise predictions of the standard model and our even more precise experimental measurements could be the first detectable tremor from a particle vibrating in a direction we cannot see. We are searching for the hidden shape of reality in the 10th decimal place of a measurement, listening for the faint dimensional harmonics in the silent music of the quantum world. The precise number 3 seems almost mundane, yet it may be the most important feature of our entire existence. Why are there exactly 3 dimensions of space? The answer could lie in a simple, ruthless principle of cosmic selection. In a universe with only 2 spatial dimensions, the story of life would be impossibly simple. An intricate circulatory or nervous system would be a logical impossibility, as any complex network of tubes or wires would be severed by the crossing of another path. There would be no inside or outside in a way that could support metabolism or a complex brain. A 2-dimensional universe is likely too impoverished, too flat to host any form of conscious observer. Now consider the opposite extreme. A universe with 4 large spatial dimensions introduces a terrifying instability into the very fabric of reality. The fundamental forces would operate under different mathematical rules. Sir Isaac Newton's law of gravity, for instance, would follow an inverse cube law instead of an inverse square law. This single change would be catastrophic for cosmic structure. The stable, elliptical orbits of planets around stars would become impossible. a planet's path would either spiral inward into a fiery death or drift outward into the frozen void. Solar systems as we know them could not form. The very atoms that build our world would also unravel. The delicate balance of the electromagnetic force that keeps electrons in a stable cloud around the atomic nucleus would also shift. Chemistry, the entire foundation of molecular complexity and life itself, would be utterly different and likely far too simple or too chaotic to produce the intricate structures of DNA and proteins. This leads to a profound and controversial idea, the anthropic principle. In a vast multiverse, a cosmic landscape where every possible number of dimensions and set of physical laws is realized, observers can only arise in those rare Goldilocks pockets where conditions are just right. We do not find ourselves in a two-dimensional flatland or a four-dimensional chaos because such universes are sterile. We are here because this specific three-dimensional geometry allows for stable planets, complex chemistry, and ultimately us. Is this a profound explanation for our reality, or is it a philosophical cop-out? Critics argue the anthropic principle simply explains away the problem, replacing the question of why the universe is this way with the tautology that we are here to see it. It can feel like a surrender, an admission that we cannot find a deeper, more fundamental reason for our three-dimensional home, yet its proponents see it as the ultimate expression of scientific humility. In an unimaginably vast cosmos of possibilities, our existence is not a central fact but a local observation, a single data point in an infinite ensemble of realities. The three dimensions we call home might not be special or chosen. They might simply be viable, the only stage upon which our particular cosmic drama can possibly be performed. The grand architecture of hidden dimensions must ultimately leave a mark on our world. Phenomenological models are the crucial bridge between these profound mathematical theories and the hard physical data from our experiments. Theorists craft these frameworks to be testable, designing specific brain world scenarios that predict unique, observable effects we can hunt for. One of the most direct predictions involves the graviton. In models with large extra dimensions, the graviton, the particle that carries gravity, is not a single entity. It manifests as an entire tower of heavier, resonant states, often called Kaluza-Klein gravitons. Think of them as the echoes of a single gravitational note played in a large, unseen chamber. These fat gravitons, as they are sometimes described, would carry the signature of the bulk, size, and shape. At a particle collider like the Large Hadron Collider, if two standard model particles collide with enough energy, they could potentially radiate one of these heavy gravitons directly into the extra dimensions. From our perspective on the brain, the result would be a dramatic and inexplicable deficit of energy. The collision would appear unbalanced, as if a significant portion of the energy simply vanished from our universe. This missing energy signal is a clear, smoking gun that physicists are actively searching for in the petabytes of data from particle collisions. Another pathway involves the direct creation of new particles tied to the geometry of the brain itself. Specific brain world models predict that the violent collisions could excite vibrations of the brain we live on. These vibrations would appear to us as new, heavy, resonating particles. Their discovery would not just add a new entry to the particle zoo, it would be proof that our entire universe is a dynamic, physical membrane. Beyond the high-energy frontier, a quieter but equally profound search is underway. If there are large extra dimensions, the force of gravity must deviate from its classic behavior at incredibly small distances. Our familiar inverse square law, where gravity's strength weakens with the square of the distance, is a direct consequence of living in three spacious dimensions. If gravity can spread into even one additional large dimension, its power would fade more slowly at microscopic scales. To test this, scientists have built exquisitely sensitive tabletop experiments. They measure the gravitational attraction between objects separated by gaps smaller than a human hair. Any detected deviation, any persistent measurement showing that gravity is slightly stronger than expected at these tiny distances would be a monumental breakthrough. It would confirm that we are sensing the gravitational field beginning to spread out or fatten into a hidden dimension. Each of these phenomenological approaches turns abstract geometry into a measurable quantity. The precise energy of a missing event, the mass of a new resonance, the exact exponent in the gravitational force law. These numbers are the clues that will ultimately confirm or rule out the existence of the cosmic bulk, revealing whether our reality is a solitary stage or a single page in a much larger book. The deep structure of reality seems to obey a mathematical elegance so precise it feels like a cosmic command. For a theory of physics to be logically consistent, its equations must balance perfectly with no loose ends or infinite contradictions. This demand for mathematical harmony is one of the most powerful drivers for the existence of hidden dimensions. In the quantum realm, theories are built on symmetries and principles that must hold under all conditions. But when physicists tried to merge gravity with the other forces, they encountered devastating mathematical flaws called anomalies. An anomaly is a kind of cancerous inconsistency where the quantum calculations that should perfectly cancel out instead produce a nonsensical, infinite result, breaking the sacred symmetries that define the theory. It is like a perfectly designed watch that, when wound, suddenly flies apart because one tiny gear is incompatible with all the others. The miraculous discovery was that these fatal anomalies do not occur in just any number of dimensions. They cancel themselves out, vanishing into perfect zero only in very specific dimensional setups. For the superstrings of string theory, the equations become clean and anomaly-free only in 10 dimensions. It is as if the universe's blueprint is mathematically impossible to draw in 3 dimensions of space and 1 of time. The numbers simply do not add up. The requirement for extra dimensions is not a choice. It is a mathematical necessity for a sane and self-consistent cosmos. This same drive for consistency introduces supersymmetry, a deep partnership between matter and force particles. Supersymmetry tames the wild quantum fluctuations that would otherwise make the mass of the Higgs boson, and by extension all other particle masses, astronomically large. This is the infamous hierarchy problem, the puzzle of why gravity is so weak compared to the other forces. Supersymmetry naturally cancels these quantum corrections, stabilizing the vast gap between the scales. But supersymmetry itself finds its most natural, and in some cases only, consistent home in higher dimensional theories. The beautiful equations of supersymmetry weave together seamlessly with the geometry of extra dimensions, each strengthening the other. The curled-up Kaluza-Klein shapes provide the perfect stage for supersymmetric strings to vibrate, and in return, supersymmetry stabilizes those very shapes, preventing them from collapsing. This symbiotic relationship suggests that what we perceive as the laws of physics, the masses and forces we measure, are really the downstream effects of this deeper, hidden mathematical harmony. Why does beautiful math so often point toward higher dimensions? It may be that elegance is not just a human aesthetic preference but a guide to truth. The universe appears to be written in a language where consistency, symmetry, and dimensionality are inextricably linked, forcing us to look beyond the familiar 3 to find the complete, coherent story of everything. The universe did not begin with its extra dimensions already curled into their tiny, hidden state. This compactification was a dramatic, dynamic process, a cosmic cooling and settling that occurred in the fiery first moments of reality. The specific mechanism that forced these dimensions to shrink while our 3 expanded is one of the deepest puzzles. One compelling idea is that the fabric of spacetime itself is subject to a kind of tension, much like the surface of a soap bubble. This inherent tension drives all dimensions to contract, but in the earliest, most energetic phase, a powerful repulsive force, perhaps driven by a field similar to the one that caused cosmic inflation, gave our three spatial dimensions a temporary but decisive push. These three dimensions were flung outward, expanding at a phenomenal rate, while the others, lacking that same initial kick, succumbed to the background tension and collapsed down to the quantum scale. The outcome was a cosmic accident of unimaginable proportions, a random fluctuation that determined the entire character of our visible reality. The stability of this configuration is another matter entirely. Why don't these tiny dimensions simply collapse further into nothingness or suddenly spring back to a large size? The answer lies in the ceaseless churn of the quantum vacuum. At the very smallest scales, virtual particles constantly flicker in and out of existence, generating a subtle pressure that acts like a supporting cushion. This quantum pressure can find a perfect balance with the contracting force, creating a stable, equilibrium size for the curled-up dimensions. The precise shape and size are locked in by these competing effects, a delicate dance that has held firm for billions of years. Describing this intricate landscape requires a new kind of field, known to physicists as a moduli field. Think of a moduli field as a cosmic dial or a control slider. Each moduli field corresponds to a different aspect of the hidden dimensions, one dial for the overall size, another for a specific type of twist or curvature. Turning the dial changes the geometry of the compactified space. In the early universe, these moduli fields were wildly fluctuating, causing the size and shape of the extra dimensions to vary chaotically. The cosmological implications of this are staggering. As these moduli fields eventually settled down to their stable values, they did not just define the geometry of hidden space. They also fixed the fundamental constants of our universe: the mass of the electron, the strength of gravity, the charge of a proton. All of these are determined by the final, frozen settings of these cosmic dials. This means the final act of compactification did not just hide dimensions, it wrote the laws of physics as we know them. The lingering energy from this settling process might even have fueled the heat of the Big Bang or seeded the first structures in the cosmos, forever linking the vastness of our expanding universe to the silent, shrunken geometry of the dimensions we lost. These cosmic strings cannot simply float freely in the void. They require an anchor, a boundary where their vibrations can be pinned down. Enter the D-brane, a surface where an open string must end, its endpoints stuck like pins on a cosmic corkboard. This simple rule gives physical shape to the higher dimensional landscape. A D-brane can have any number of spatial dimensions. A D0 brane is a point. A D1 brane is a line. A D2 brane is a sheet. Our entire universe could be a D3 brane, a vast three-dimensional island where all the open strings of matter are permanently attached. This single idea transforms the abstract concept of a brane into a concrete, physical object defined by the strings that end on it. The properties of the particles we see are directly tied to their confinement. An electron is not a particle that can wander off into the bulk. It is an open string whose ends are forever stuck to our brain, vibrating in place and giving it mass and charge. This explains with stunning elegance why we are so exquisitely tuned to three spatial dimensions. We are made of stuff that cannot leave the surface we call home. But what about the strings that form closed loops? These closed strings have no endpoints to pin down. They are free to detach from any brane and propagate through the entire higher dimensional bulk. And what force is carried by a closed string? Gravity. The graviton is a closed string. This is the ultimate reason gravity feels so different, so weak and pervasive. It is the only fundamental force that is not stuck to our brain. It is the lone wanderer, its influence diluted across the full expanse of the hidden dimensions. The specific configuration of these D-branes then becomes the engine of reality. How many branes are there? How are they stacked, wrapped, or intersecting within the compactified space? Each possible arrangement defines a different possible universe with a different set of particles and forces. The most profound possibility involves brane intersections. Picture two sheets of paper, our D3 branes, slicing through each other at specific angles within the curled-up geometry. Where they cross, the open strings that define our reality gain new properties. These intersection points can act as trapping sites for specific vibrational patterns of the strings. Remarkably, this can naturally generate the family structure we observe in the standard model of particle physics. We do not have just one electron. We have 3 generations of electrons, each heavier than the last. We have 3 generations of quarks. Why 3? The answer might be that the particular Kaluza-Klein manifold our universe is built upon forces our brain to intersect with other branes in exactly 3 distinct locations. Each intersection point gives rise to 1 generation of matter. The entire zoo of particles, with its puzzling repetition, could be a direct map of how our local brain is woven through the hidden dimensional geometry. The search for the one true vacuum, the one configuration that matches our world, becomes a search for the specific arrangement of D branes whose intersecting symphony produces every note we have ever detected. A sheet of carbon just 1 atom thick can shatter our ideas of dimension. Physicists studying graphene, a miraculous material made of a single layer of carbon atoms arranged in a hexagonal lattice, found something astonishing. The electrons racing across its surface did not behave like ordinary particles in a flat, 2-dimensional plane. Their interactions were governed by mathematical equations that perfectly describe the behavior of particles living in a space with an effective extra dimension. This is not science fiction. It is a laboratory reality known as an emergent dimension. The graphene sheet itself is physically 2-dimensional, but the quantum fields that control the electrons within it generate properties that are mathematically identical to those of a higher dimensional system. It is as if the material contains a hidden, imaginary direction that influences everything that happens on its surface. This discovery opens a breathtaking new front in the hunt for hidden dimensions. We may not need a particle accelerator to find them. We might simply need to look closer at the exotic materials we can create here on Earth. This connection extends far beyond graphene to a whole class of substances known as topological insulators. These are materials that are electrical insulators in their interior but conduct electricity perfectly along their surface. The electrons on the surface of a topological insulator are protected from scattering by a powerful quantum principle, allowing them to flow without resistance. The mathematical description of these flowing surface states is once again identical to the theory of massless particles living in a higher dimensional space. By studying the strange and robust electrical currents on the surface of this 3-dimensional crystal, physicists are effectively probing the physics of a hypothetical 4-dimensional world. This is more than just a clever analogy. It is a profound duality. The complex quantum interactions between billions upon billions of atoms in a carefully engineered material can give rise to collective behaviors that mimic the laws of a universe with more dimensions. These are emergent phenomena where the whole becomes far greater than the sum of its parts. The dimension is not fundamentally real in the way that our 3 spatial dimensions are. It emerges from the intricate dance of quantum mechanics across a vast ensemble of particles. Why does this matter for the cosmos? These laboratory simulations act as testing grounds for ideas that are otherwise impossible to experiment with. We cannot build a particle collider large enough to probe the compactified dimensions of string theory directly, but we might be able to design a material whose electrical properties are governed by the same equations. By measuring the flow of current or the response of the material to a magnetic field, we can test the predictions of these high-dimensional theories in a benchtop experiment. The quantum Hall effect, a bizarre phenomenon where electrical resistance in a 2-dimensional material becomes quantized into exact steps, is described by a mathematical framework that is deeply connected to topological quantum field theories in higher dimensions. Each precise step in resistance is a direct signature of a topological invariant, a number that reflects the effective shape of an unseen dimensional landscape. So the next time you hear about a new wonder material with impossible properties, remember that its magic might not be confined to our three familiar dimensions. It could be a tiny working model of a grander cosmic architecture, a whisper from the bulk made audible in the hum of electric current. These hidden dimensions force a profound philosophical question. What is reality, and how much of it are we truly equipped to perceive? Our senses and our instruments are built to navigate a world of three spatial dimensions. We are like the prisoners in Plato's famous allegory, chained in a cave from birth, seeing only the shadows cast on the wall by a fire behind us. We take those flickering two-dimensional shadows for the entirety of existence, never suspecting the rich, three-dimensional world that casts them. The theories of hidden dimensions suggest we are in a similar prison, mistaking our four-dimensional slice of space-time for the whole cosmos. The true reality, with its 10 or 11 dimensions, is the world outside the cave, casting the shadows we mistake for fundamental particles and forces. This is not just a metaphor for knowledge, but a potential description of our physical situation. We are cave dwellers, and the curled-up Kaluza-Klein manifolds, the warped bulks, and the intersecting branes are the true forms we can only infer through mathematical reasoning. This leads to a deep puzzle about mathematics itself. Are these intricate dimensional geometries something we invent, a beautiful human construct to make sense of the world? Or are we discovering them, uncovering a pre-existing objective architecture of the cosmos? The uncanny way that pure mathematical necessity, the demand for logical consistency, forces the existence of extra dimensions suggests we are explorers, not creators. The universe seems to be written in a mathematical language, and we are slowly learning to read it one dimension at a time. The most profound implication touches the nature of consciousness and existence. Could our awareness, our sense of self, be a phenomenon that is not confined to our three-dimensional brain? If our minds are ultimately patterns of information, and information itself may be fundamental, as the holographic principle suggests, then consciousness might be a process that is rooted in the full, higher-dimensional reality. We experience it in a linear, three-dimensional way, but its true substrate could extend into the bulk. Perhaps the feeling of a unified self, the mysterious hard problem of consciousness, arises from a deeper integration across dimensions we cannot consciously access. This idea transforms our place in the cosmos. We are not merely biological machines on a rocky planet. We may be multidimensional beings, experiencing only a narrow, filtered projection of a vastly richer existence. The search for hidden dimensions is therefore more than a scientific quest. It is the ultimate attempt to step out of the cave and glimpse the true, staggering nature of the fire that casts all the shadows. Our journey into the unseen did not begin with particle accelerators. The very idea of dimensions has been reshaped across centuries, evolving from abstract geometry into the cornerstone of cosmic reality. Ancient Greek mathematicians like Euclid laid the groundwork, defining the point, the line, and the plane with a logical purity that described a perfect three-dimensional world. But it was a Victorian schoolmaster and theologian, Edwin Abbott, who truly opened the public mind to dimensional possibilities. In his 1884 novella Flatland, Abbott crafted a brilliant allegory of a two-dimensional world inhabited by geometric shapes. Through the eyes of a square, we experience the shock and awe of encountering a three-dimensional sphere, a being who can see inside closed buildings and lift shapes out of their plane. Flatland was more than a mathematical curiosity, it was a profound lesson in perspective. It forced readers to confront the limitations of their own perception, asking a haunting question. If a two-dimensional being cannot comprehend the third dimension, how can we be so sure that our three-dimensional view is complete? This simple story planted a vital seed, preparing the cultural ground for scientific revolutions to come. The next great leap was purely mathematical. In the early 20th century, Theodore Kaluza and Kaluza-Klein made the breathtaking discovery that adding a single extra dimension to Einstein's equations of gravity could produce the laws of electromagnetism. Their work was a formal, rigorous proof that hidden dimensions were not just philosophical speculation, but a potential feature of physical law. Yet this idea languished for decades, a beautiful theory without an experimental home. The technology of the era simply could not probe the tiny scales where Klein proposed his dimension was curled up. It was only with the rise of string theory in the latter half of the 20th century that the concept exploded back into prominence. The mathematics demanded more room, and physicists had the computational power to explore the intricate shapes of Calabi-Yau manifolds. Each generation's tools have directly shaped its dimensional theories. The compass and straightedge gave us Euclid's perfect forms, the thought experiment gave us Abbott's flatland, pen and paper gave us Kaluza-Klein, and supercomputers now give us the string theory landscape. Our vision of the cosmos is forever limited and liberated by the lenses through which we choose to look. We have moved from drawing lines in sand to simulating the birth of universes in silicon. And with each new tool, the hidden architecture of reality reveals another layer of its stunning depth. This final frontier is not an end but a threshold. The next generation of experiments is being designed with one explicit goal: to find the cracks in our three-dimensional reality. Future particle colliders, like the proposed Future Circular Collider, will be colossal rings over 50 miles in circumference, smashing particles with energies far beyond today's capabilities. They will scan the debris for the faintest whispers of missing energy or the ephemeral flash of a microscopic black hole with unprecedented precision. In space, a new era is opening to the cosmos. The Laser Interferometer Space Antenna, LISA, will be a fleet of 3 spacecraft flying in a perfect triangle millions of miles apart, connected by lasers. It will detect gravitational waves from the mergers of supermassive black holes, events so powerful they shake the fabric of spacetime itself. LISA will listen for subtle distortions in these waves, a faint chorus that might carry the resonant frequencies of hidden dimensions. These are not incremental upgrades, they are leaps into the unknown, instruments built to test the geometric foundations of our universe. Beyond pure detection lies a realm of wild speculation. Could consciousness itself be a process that, in some way, taps into these higher dimensions? Our brains are complex networks of quantum and classical computation, and some theorists suggest the binding of our subjective experience might occur in a state space that transcends our familiar 3 dimensions. It is a radical thought that the feeling of self, the qualia of red or the sound of music, might be rooted in the geometric tapestry of the bulk. Even more speculative is the distant dream of dimensional engineering. If we could ever understand the modular fields that stabilize the extra dimensions, could we learn to adjust them? The ability to change the size or shape of a compactified dimension would be the ultimate technological power, a way to rewrite the laws of physics locally. You could dial the strength of gravity, change the mass of an electron, or perhaps even open a gateway to another brane. This is the stuff of cosmic fantasy, but it underscores a profound truth that understanding dimensions is not just about observation, but about potential mastery over the deepest layer of reality. We stand at the very beginning of this story. For all our mathematics and machinery, we have only just begun to suspect the true scale and complexity of the cosmic architecture. The next century of exploration promises to be the most thrilling in human history, as we move from asking if there is more to see to learning how to see it. The hidden dimensions are not a puzzle to be solved, but a new continent of reality waiting to be explored. We have traveled from a single curled-up circle to a cosmos of holograms, branes, and vibrating strings. Each of these 30 theories unveils a different facet of reality's hidden architecture, transforming our universe from a simple, 3-dimensional stage into a rich, multidimensional masterpiece. The weakness of gravity becomes a whisper from the bulk, the birth of our cosmos echoes from a brane collision, and the very laws of physics emerge from the silent geometry of Kaluza-Klein shapes. This is not just a collection of ideas, it is a fundamental shift in perspective, inviting us to see every particle, every force, and every moment of cosmic history as part of a deeper, grander whole. The journey redefines our place in existence, not as passive observers in a fixed reality, but as active participants in a cosmos of staggering depth and possibility. So we turn the question to you. Which of these visions of hidden reality resonates most deeply with your own curiosity? Was it the holographic principle, the cyclic ekpyrotic universe, or the sheer elegance of supersymmetry? Share your thoughts in the comments below, and if your mind is hungry for more mysteries that challenge the very fabric of existence, be sure to subscribe for our next exploration into the unknown.